All right. Thanks for being here. I'm grading things. I'm hoping tomorrow is going to be my big day where I sit down and grade all of the things that I have to grade. So hopefully by Thursday I'll have the exam back. Um, Fingers crossed. Um, I do have a new packet for you, because we're starting a new chapter. It's chapter 3. What chapter are we in? 3. Yeah. Which is on Eulerian and Hamiltonian graphs. So the graphs that have fairly interesting properties. I'm not going to go into, so the book it talks about like, here's what it is, and here's proofs for the theorems. I'm not going to go into the proofs. We're just going to talk about here's what it is and do the exercises. Um, and that's it. I estimate that it'll only take maybe today and Thursday to get through. So a fairly short unit. The next unit will be digraphs, directed graphs. And then after we do that, we'll look at coding. So actually like representing graphs in code, how can we do that? And then my plan for once we do that is we're going to start to look at algorithms that we can use on graphs. So once we know kind of here's like some properties of graphs and their structures, then we can look at how do we use those. That's kind of the plan. I might decide to put things between digraphs and coding just because if we want to look at more properties before we get there. So this is subject to change, but that's the general plan. We are getting to coding, I promise. All right, I'm going to pause recording so that we can do some more attendance. All right, so we're going to start to learn about these new kinds of graphs, and both of them kind of go together, but they're doing slightly different things. So there are two kinds of problems that we've got going on here. So we've got two main problems. One is what the book calls the explorer's problem, where if you think of an explorer, they're trying to look at everything. And the second is the travelers. And this will be spelled with 1 or 2 L's depending on how British we're feeling. The book is British, so they use 2 L's. But the explorer is wanting to find a tour in a graph that traverses so like, let's say we're going from one city to another. And so if this is our graph, drawn very poorly. Let's say all of the vertices are cities and all of the edges are roads. The explorer's goal is to take every road. So that traverses each road exactly once. And so take each road exactly once and then return to the starting point. So we don't want to double, like, we don't want to take a road more than once. And return to the starting point. That's the goal of an explorer. The traveler's goal is the traveler doesn't care about taking all of the roads, right? If you're traveling to a series of cities, you just care that you get to the cities. So the traveler's goal is to find a tour as well, but instead of the roads, we're looking at visiting the cities. And so in a similar way, exactly once and return to the starting point. Okay, so that's the goal of the explorer and the traveler. So let's go and label these. So A, B, C, D, E, F, G. This is our map of cities. So an explorer, so let's say we start at A. There's a couple of different ways to get there in this graph. But for example, here, let me write out I'm gonna write out the tour and then I'll draw it on the graph. So let's say, so one of the possible tours is A, B, C, D, E, F. So going all the way around. And then going back to B, detour down to G, back to C. So that takes care of this little part of it. And then E, G, F, and then back to A. So let's see that in action. So we start at A, we go B, C, D, E, F. That takes care of all of those. And then back up to B, down to G, up to C. Then back down to E, and then we do the zigzag again, and then go back to A. So G, F, and then A. And as a result of doing that, we've covered every edge in the graph. So we've covered every edge. And we've also visited some cities multiple times. Like we go to F and B multiple times, but that doesn't matter. That's not our goal. Our goal is to visit every edge, take every edge exactly once. And we do that. Great. Okay, let's look at the traveler's tour. So the one that the book has is A, B, C, D, E, G, F, A. So if we look at that, A, B, C, D, E, and then up to G, down to F, back to A. Right? So we have gone around our graph, visited every city only once. And if some edges like F, E, C, E, B, F, those are not visited, fine. We don't care about that. There's also multiples of these. So the book gives an additional explorer's tour and an additional traveler's tour. So in some graphs, there may be multiples of these. The tour may not be unique, is the way that we say that. So explorer, explorer may visit a city multiple times, and the traveler may omit roads, right? It's not what we care about for each of those. Okay, good to move on. Anyone need more time? Okay. So let's look at these in graph theory terms. So the thing that we're going to assume for these graphs is we're going to assume the graph is simple and connected. That's our assumption. So no multiple edges, no loops, and it's just all one piece. So the explorer's goal is to, so writing it in terms of the words that we know. So we're finding a tour, but what could we call this tour? Or what could we call the tour that for the traveler? Yeah, cycle. So for travelers, we're looking for a cycle. So, all right. So we're looking for a cycle that includes every vertex of the graph. And we call this one the explorer's problem to find this cycle. The name we give this is Hamiltonian. And that's the term that we're going to use going forward. So this sort of cycle is called a Hamiltonian cycle, named after a guy named Hamilton. Any ideas for explorer? So what thing can we be more specific about tour? Yeah, so that's what we're doing, but I'm trying to find out what word can we apply for tour? You are right, in fact. This is the word we're going to apply to explore. So what sort of terms do we know? We know a walk, which is just going from one edge to another, no restrictions. Yeah. A path. I would say no. Do you have an idea? Trail. Yeah. So a path, it's not a path because a path doesn't repeat vertices, and we can repeat vertices. So we're looking for a trail. I'm looking for another word there. But a trail that includes every, instead of vertex, we're looking for a trail that includes every edge of the graph. Any ideas for the word that goes here? Go back up to the. So something that traverses each road exactly once. The thing we haven't brought up is that it returns to the starting point. What's the word that we use for that? Yeah, closed. So if it started and finished somewhere else, then it would just be a trail or an open trail. But since we return to the starting point, then it's closed. And we don't have to worry about that with cycle, because the cycle inherently, the notion is that we go around vertices and go back to where we started. Awesome. So pronouncing this, I think, is difficult. It makes sense in my head, but whenever I try and say it out loud, I feel like I'll pronounce it a different way. The way you say this guy's name is Euler, so maybe it's Eulerian or Eulerian. We'll know what each other is talking about. We'll figure it out from context. Hamilton's got it easier. Okay. To help keep you like keep these two straight, just remember that Eulerian graphs are about edges. They both start with E. Unfortunately, vertex doesn't start with H, but Eulerian starts with E. Okay. Do we need more time? We're almost at our first example. Before we do that, let's, oh no, I forgot to do this. No, I would like to hide. There we go. Okay, so let's look at a few examples, and then we'll look at a packet problem. So we've got the original graph that we're looking at. Where we found an Eulerian and a Hamiltonian. We found an Eulerian tor and a Hamiltonian cycle. And that means that this graph is both Eulerian and Hamiltonian. So E check, H check. We found one of each. There's actually more than one of each. But the presence of there being one means we can say that this graph is both Eulerian and Hamiltonian. Let's look at some subgraphs of this one. Take a minute and think about this. Do we think this is... First, let's see if we can find that closed trail. Can we? Yeah. Maybe if we start here, we go down. Ah, no. And then back up. Great. So now I would like to erase that. Eulerian, check. Is it Hamiltonian? See a yes and a no. Okay, it's now a no. Right, because the way that we got the Eulerian trail is we go back down it, but we repeat the middle vertex. And so because of that, like that's the only way that you're gonna get anything done here. So this graph is not Hamiltonian. What about just take that middle subgraph and add back in those vertical edges? What about this one? Yeah. I feel like the only way that we get around that is just practicing saying it. Why isn't it? Yeah. Yeah, okay. We'll talk about that. Like that's the answer that the packet problems are building to. Great job. Do we have like an intuitive answer for how? So like, let's say we start here. If I go around, well, maybe I can go here now instead of going back to the start. But then I can't get this edge and go back. That's not allowed. So yeah, this graph is in fact not Eulerian. Is it Hamiltonian? Yeah? How come? It is. Yeah.
Usually goes to every.
You can easily go to every vertex. So maybe like if we start here, we go around. Now we can go in and then take that last edge. Yeah, that makes sense to me. Great. So it's Hamiltonian. All right, let's look at one more. Did I get everything? I think so. What about this one? Yeah. Why not?
Just by like the color structure in the middle, you know, it can't be. And it can't be Eulerian because those two vertices at like the very end,
Mm-hmm.
they only have a degree of 1, so it means that you can't cycle back to them without traversing the same edge. That's
Mm-hmm. And it's not possible if we like start from one of here.
have to be, if the graph is Eulerian or Hamiltonian, you have to, it's closed. You have to cycle
Mm-hmm.
back to it.
Oh, yeah, yeah. Because it's closed. So we could, in theory, have, or maybe not. I was thinking maybe we could like start here and go to the end. But yeah, so for these guys, you can't start here and then go back. And we've got this subgraph, which we saw wasn't Hamiltonian. So yeah, this one is in fact neither. Awesome. So now there's packet problem, which is just more of the same, right? So try and figure out which one of these are Eulerian or Hamiltonian, and then if it's one of them, then write down one of the cycles. There may be multiple, but just write down one of them. Yeah. All right, I'll give you 1 more minute. Okay, let's look at them. What about A? Is it Eulerian? Thumbs up or thumbs down? Thumbs down. That's correct. Because yeah, because like B has an odd degree, so we have to be able to go there and then go out multiple times for every edge to be covered. So it's not Eulerian. Is it Hamiltonian? Yeah. We could go, let's see, can I make it smaller? Yes. So if we start at A, great, we got it. Okay, what about B? Eulerian? Some thumbs up? Yeah. Let's see. The one in the book has A, B, C, D. And then back up to, wait, no, around to E. Back up to A. And then we do the star. And then all the way up. So we can visit A if we're just not done with it yet. So we're like, we're not barred from A if that doesn't count as us returning to the starting point. Only once we've covered all the edges. So yeah. What about Hamiltonian? Yeah? Yeah. I mean, the simplest way is to just do the cycle all the way around and ignore all the stuff in the middle. What about C? Eulerian? Thumbs down? Why not? We've got this, it's a 3 regular graph, right? So we've got later. I'll assign it to Zoom later. So yeah, so we've got to have a way to get back. So not Eulerian. What about Hamiltonian? Yeah. Let's see. If we could like go in here and down and then go that way. That's one possible way of doing it. So yes. What about D? Eulerian? Yes. Hamiltonian? Yes. E. What do you think about E? Eulerian? Okay, I have conflicting information. Why do you think?
One slash two.
So B, wait. Oh, E, yeah, sorry. I did not see it. I thought that was a C. Okay, so if we start here and just go. So this one, in fact, wait, this is E, make sure I get this, yeah. It's not Eulerian. What about Hamiltonian? Thumbs down? Right, if we start at the bottom, we'll get back up to one of the two on the top and have no way to get there. If we start at the top, well, well, we'll go back up to B, and that's not acceptable. So, no, it's not Hamiltonian. What about F? Eulerian? See a thumbs down? Do we agree? F, yeah, it's not Eulerian. Is it Hamiltonian? Yeah. For this one, we can start at any of them and just maybe follow the edges. Whoops, no. Sorry, there's a button on my pen that erases it, which is too easy to press. Yeah, that's one possible Hamiltonian cycle. So, yes. What about this last one? This one may look familiar. Is it Eulerian? No. Is it Hamiltonian? Yeah. It's pretty easy to see. You could like take two edges down, go to B, back to A. That's easy. Which one is this? What's this special graph called? Do we remember? G. You know it. Königsberg? Königsberg? Another word that I do not know how to pronounce. Yeah, this is that bridge problem where people were wondering, can we cross every bridge? And since it's not Eulerian, we can't. It's not possible. So the term they were looking for is Eulerian, and Euler was the one who was like, no, you can't do it. So they named that after him. Awesome. Thank you. So the next step is to talk about each of these in a little bit more detail, look at some theorems around both of them. The bridge problem in particular, this is the packet problem 2, where finding a route crossing each bridge just once and returning to the starting point, so finding an Eulerian trail, is possible only when the following condition is satisfied. So this is a conjecture that's given to you. Whenever you cross into a part of the city, so into one of the vertices, you must be able to leave it by another bridge. And so the question is, what does this tell you about the degrees in an Eulerian graph? We've talked about this. Yeah, it's got to be even. And so then using that, I think this seems to like follow immediately directly. But what's the rule that on a given graph is Eulerian? So we say that vertex degrees are even, then in an Eulerian graph, every vertex has even degree. So that means we need to show that every single vertex. How do we show that that something is not Eulerian then? Yeah. If it has odd degree, and can we say anything more specific about that? I'm wondering what's it? Spell degree correctly. The vertex? Yeah, so the opposite of every is like every vertex has even degree. The opposite of that statement is that, yeah, at least one. Yeah, so since everything needs to have even degree, if there's at least one vertex with odd degree, then it's not Eulerian. Okay, so take a second and convince yourself that this property holds for these ones, for the Eulerian side of it, at least. It is got a vertex of degree 3, not Eulerian. B, no vertex of odd degree is Eulerian. E's got a vertex of degree 3, thumbs down, and so on. So that's our rule. Let me resituate these here. So we can write this as a theorem. So the book numbers it theorem 3.1, which says, let's start with a graph that has all even degrees. So let G be a graph. Um, all of whose vertices have even degree. So this is our starting point. And then, oh, the book splits this up into multiple steps. So the book step, so like we have the answer, but the book splits it up to then G can be split into cycles. No two of which have an edge in common. So let's look at this one. This was Eulerian, right? So we can split it into cycles which don't share an edge. Like this is C1, that's C2. Yeah, I'm not a huge fan of how they structured this one. I feel like we got the intuitive definition, and so then we should just go with it. But alas. So the next problem is how do we split this one into cycles? Let's see what the book says. Okay, so one of the options that the book gives, so if you do this, you may come up with something different. We've got C1 here, which is this triangle. We've got, and now we can't do like this cycle because we've used up that edge. This could be C2. This could be C3. And this can be C4. In such a way where now we've used up all the edges of the graph. Okay, so now if I give us another page. So the theorem that we actually care about is connected graph is Eulerian if and only if each vertex has even degree. A note on this notation, the IFF, that's not a typo. It means if and only if, it just gets abbreviated to IFF. And what this is doing is this is showing a bijection. So we're going from one thing to the other, and we can also go from the other thing to the original thing. So let's say G is Eulerian. That's one statement on one side of this. And then each vertex is even is on the other side of that. So one thing, IFF, the other thing. And so this actually gives us two statements. So it gives us if we had pretended that we only gave it one if, then a connected graph is Eulerian if each vertex has even degree. And so the way that we write that is each vertex even implies that G is Eulerian. But if we didn't have going the other way, we can't say that every Eulerian graph has even degree. We can only say the ones, this graph with even vertices is Eulerian. So having the other way means that G is Eulerian implies that each vertex is even. So there's two statements in here. Okay. There's another packet problem. Which is just to try and verify for a second. So like, remember K is the complete graph where all edges possible are there. This is the complete bipartite graph. Where we have 1, 2, 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. And all the edges possible are drawn between the two. but not inside each of the 8. Okay, ignore E. But at least let's at least try C and A to just verify that. Okay. Did we verify them? K8? Yes. C8? Oh, wait. K8 is not? No? Great. Oh, right, because it's not determining that they are, it's determining which of them are. What about C8? Yeah. Awesome. Okay, we'll move on. So we'll talk about semi-Eulerian. The book gives theorem 3.3, which just combines 1 and 2 of an Eulerian graph can be split into cycles with the rest of that. But I feel like we covered it with 3.2, so I will move on. Okay, so the next packet problem asks about semi-Eulerian, which is just where we start and end at different places. So if all of the other properties are fulfilled, then we can just start and end somewhere else. So this is actually saying if there exists an open trail, so open instead of closed, that includes every edge. And that trail is called a semi-Eulerian trail. So it meets the Eulerian definition that we've hit every edge, but it's semi because we didn't go back to the starting point. And there's a theorem about this, which again, we're not going to prove. But if you would like to know the proof, it's in the textbook. And the theorem is 3.4, which is a connected graph is semi-Eulerian if and only if, so we see this again, if and only if it has exactly two vertices of odd degree. So that's our theorem for this. So if there's exactly two vertices with odd degree, then it's semi-Eulerian. Otherwise, it's not. So only if we have exactly two with odd degree is it semi-Eulerian. Otherwise, if there's one or three or every, then no. Okay. So let's end with, we'll do problem 5. I'll give you a few minutes. And then we'll talk about the homework and then be done for the day. Then we'll start up with Hamiltonian next time. So take a few minutes to do problem 5, then we'll talk about it. The definition you missed. Let me show you. So the semi-Eulerian is if we don't start and end at the same place. All right. Is A? Yeah. Do you have a trail for me?
From A to B, E to B, B to C, C to A to B, and B to B.
A to E, E to B, B to C, C to A, back down, back up. Yeah, start and end at different places, but otherwise we can cover all of them. What about B? No? Yep. It's got 4 vertices of odd degree. 1, 2, 3, 4, which is all of them. And so since there's more than 2, then thumbs down. What about C? Yeah? The one the book has is very long. And the one you probably have is also very long. So maybe I'll leave that to you and you can check in the book. But yeah, this one is. So what are the vertices with odd degree? 1, 2, 3, 4, 5, W and Z. Is that it? Yeah. So since there's exactly 2, we can find a trail and there we go. Okay, so the plan is next time we'll cover Hamiltonian. That may not take the whole class, so we might start digraphs next time. I'll prepare for that. I want to tell you that the homework is posted. I have to fix the math rendering on this. But there's 4 problems. So I've got the one that I wrote of, which I really enjoy, of find some application for this. So like maybe go out in the wild and find a graph that turns out to be either Eulerian and or is Hamiltonian. And so I want to make sure that you put some thought into it. So I have a restriction of maybe at least 20 words to explain it and a graph drawing. And then some problems from the book for verifying are these Eulerian, for what values. After today, I'll go through and fix the math rendering. Problem 4 is we'll talk about Hamiltonian. But like for which values does this apply? And then the last one is to draw a graph that is one but not the other, and then is the other but not the one. So that's assigned. Tentatively, it's due March 18th, which is next Tuesday. So get started on it. Depending on how things go, I might make time at the end of class tomorrow to work on it, but we'll see. So start working on it. And remember, the homeworks are individual but collaborative. So work with your classmates. Everyone should write their own paper, but you can work together and brainstorm, please. Any questions before we end? All right. Thanks for being here. See you on Thursday.